We are being recorded. And let me share my screen briefly to welcome you to the Kickstarter Colloquium series. This is one of our final instances of the series. I believe we have one additional talk scheduled in January. We also will reach out again to all the members to all the people that were supported by the Hayes and Simon Foundation grant that enable the Kickstarters who have not been able to speak yet. So if you have not been able to speak in this series and you want to do that, keep an eye out for emails and Slack messages from myself and Rachel. We'll try to schedule you again for the new year. As a reminder, these Kickstarter projects were supported through a grant of the Hayes and Simon Foundation entrusted to Las Cumbres Observatory, and to be used to support 3 of the 8 science collaborations of Rubin-LSST, namely the Transcendent and Variable Star Science Collaboration, Stars Milky Way Local Volume Science Collaboration, and Solar System Science Collaborations. Those 3 areas of research being the ones that are closest to the areas of research that traditionally the Hayes and Simon Foundation has supported. We use this grant for publication charges, infrastructural development, and training for the members of the science collaborations, but we devoted the majority of the grant to a competitive process of proposals through which we funded just over 40 proposals, which we called Kickstarter projects. And here we're going to hear about 2 of them. The Blanco DECam Bulge survey, a Rubin crowded field Pathfinder project on DECam. Dr. Michael Rich is going to speak about this project. And stellar variability with Rubin-LSST. Dr. Matteo Monelli is going to speak about this project. To the speakers, we're going to split the hour in a half, about 10 minutes have already gone. So you have about 25 minutes for your entire presentation. I will give you a heads up when we are at the 18 minutes mark. And with that, Michael, if you want to take it away, I think you should be able to share your screen.
Okay, I'm just looking to find the share screen, which has suddenly disappeared. So I'm just going to exit my talk and try to find the share screen. Here we go.
It looks like it's on. Oh, okay. Now we see.
You see the.
We see the slide deck. We don't see it in presentation mode yet. Let's see if that works.
Yes, I'm just trying to do that so that. Okay, here we go.
So.
Thank you.
Very good.
You see the. You see it properly, not the.
Yeah.
Okay. Okay.
Good to go.
So first of all, I wanted to thank the Hayes and Simons Foundation for the financial support of this project. And unfortunately, we're not going to be able to present the results of our proposed investigation today. But instead, I'll talk about the inspiration for it and some of what we were able to do. This is an image of the galactic bulge, and it's an extremely crowded field. This is the kind of field that the LSST pipeline was not designed to handle. And so what we had proposed to do was to try to get the LSST crowded field pipeline, the actual pipeline, up and running, reduce a series of fields, and then use those same fields to do the reductions that I'll be describing shortly using Christian Johnson's pipeline, which uses ALLFRAME and Daophot, which is the state-of-the-art standard for reduction of crowded field photometry. Now, what we did do was that Professor Marcus Robus is at La Universidad de la Santísima Concepción, Chile. Now, this is a university that serves very an underrepresented population, many of which is indigenous in Chile. They really serve students coming from the bottom 50% of the income distribution in Chile. And historically, virtually none of them or members of their family have been to university before. This poses a challenge. First of all, Professor Rabus was arriving there during the height of COVID and having to set up a whole teaching and research organization. And then he went further and reached out to a junior scientist in Argentina and involved her in the project. Now, what happened was that there were multiple challenges. Ultimately, it was not possible to get the computing resources at Concepcion. So we looked to link at University of Washington. And it's still at the end of the project while 5 undergraduate students were involved and learned about the science aims of the project, as did the colleague in Argentina. We were only able to do an initial test analysis on a postage stamp. However, the project continues. The problem was that the idea was first to successfully reduce the data with the pipeline, and then Christian Johnson at SDSCI would take the identical 6 fields of different crowding in G and R, produce color magnitude diagrams and luminosity functions. And the idea was for a student at UCLA then to compare the 2 results under my direction. And unfortunately, the first part of the project didn't happen. And Christian Johnson at Space Telescope Science Institute has many functional duties. And without identifying the test fields, even we did not do the project yet. However, it is very much our intention to continue doing this project until we get a result. The way I came to this project was that I had approached Zilko Ivajic, who's also a member of the BDBS collaboration, and said, what are we going to do about the Milky Way at LSST? And initial efforts to look at how the pipeline functioned, and this was about 3 years ago, the pipeline could not even begin to address crowded stellar fields. So this project, which actually originated before 2020, was inspired by working on the galactic bulge with DECam. The only test data that we have today is from the dark energy camera. Of course, we do not have a commissioning camera in the Rubin telescope yet, though I understand that there will no longer be a commissioning camera campaign, but the actual science camera is intended to go in, and commissioning will use the science camera. Is that correct, Federica?
That is correct. We will
when,
go on sky directly with LSST CAM.
And when is that presently planned to go ahead?
So there's a whole presentation that I recommend anybody that is interested in this to look at. It's on the Rubin Project Science Team Science Collaboration YouTube channel. The calendar details are being refined, and they will soon be published on ls.st/dates. So I'm not going to tell you a date right now. I'm just going to point you to that. But compared to what we expected for ComCam to go on sky, LSST will go on sky roughly 4 months later. That's the current forecast.
Yeah, well, it's very exciting. And so sometime perhaps within a year, we'll be seeing the first data. Until then, there's a great deal of data that has been taken with the 4-meter Blanco telescope and the the dark energy camera funded by the Department of Energy. Does not do nuclear fusion, by the way, but anyway, that camera is at prime focus, and you could see presently it's the largest field astronomical camera on a large telescope. And you could see that this cabling feeds both electricity and liquid nitrogen into the camera. I have used the camera within the last year, and it is definitely showing its age. So the goal of this was to map a solid field of the sky in the Southern Galactic Bulge. And while there have been a great deal of infrared observations of the bulge from the variables in the Via Lactea survey, that has been in JHK, the infrared, and optical colors are much better for use in when one does interested in metallicities and ages of stars. It's much more sensitive for reasons that I'll show you shortly. And this shows some of our publications from this survey. So we do know how to do photometry, and this is an interesting survey. The question is, in comparing to try to directly compare head to head the pipeline performance, we need to actually identify individual fields. Christian Johnson had done this in terms of a large database where the data are merged and served out of a server very similar to the way LSST will be eventually, but we actually need to go back and re-reduce a set of fields. Now, the science goals here are driven by a controversy that has occurred by several controversies, one of which is this plot here shows the derived ages for microlens subdwarfs down here on the x-axis versus their metallicity on the y-axis. And you'll notice that there is something quite jarring about this plot, and that is that there are an implied large number of stars, even younger than 1 billion years old in the bulge, as you can see on the right. Now, many other studies of the bulge with HST had suggested that particularly in small fields, that the bulge is extremely old, at least as old, dominated by stars as old as globular clusters. And this result contradicted what appeared to be a well-established fact in the literature. And so that was one of the major drivers. And the other was a desire to try to measure the structure of the bulge as a function of metallicity. And here is the footprint in yellow that has been reduced. We still have not reduced these other fields here, but this entire contiguous area has been reduced. It's not a perfect rectangle because we didn't get neither sufficient time allocated nor clear nights to allow the observations in all filter band passes. Now, one of the unique, there are other surveys that have done this kind of work, notably something called DECaps, but we're unique in having obtained very short exposures. And these are necessary in order to not saturate the brightest giants that are still members of the galactic bulge, but that red colors can be as bright as 11th magnitude and therefore required exposure shorter than 1 second. The problem of saturation will be an issue for these stars with the Rubin Observatory. I'm not quite sure how that's going to be handled. There are many globular clusters in this contiguous footprint. We have not yet made the data public. We are hoping to get funded. This is all of the science, an NSF grant funded the reductions and acquisition of the data originally. No science has been funded by the NSF, but we're hoping to try to make the data public soon. This shows how our interlocking each one of these little hexagons represents a field of the camera, and here you can see it superimposed on a reddening map. So we are reaching into, and notice this is EJ minus K. Our survey, therefore, covers a large fraction of the bulk of luminosity, here illustrated in 2 microns, and also reaches into highly reddened fields. I'm just going to briefly just call out some people who made major assistance here. Scott Michael, who's no longer with the project, unfortunately, has moved to industry, and also Kathy Vivas at CTIO, who assisted with setup and observations. Justin Cater, who's moved into a different subject area in astronomy. Andrea Kunder, who is at St. Mary's University in near Seattle, which is another relatively small institution, but he has a great undergraduate group and been working very actively on the project. All of the reductions here were done by Christian Johnson at Space Telescope Science Institute, 50 terabytes of data. And once we get the pipeline to perform, he will then be in charge. He has recently written an improved code, which should really challenge the crowded field pipeline and give it a run for its money. So I'm definitely going to pursue this. This shows, this is maybe of some interest into how the project goes. If the data comes in through the archive and then NOAO archive, and then goes to the Pervasive Technology Institute, which is a supercomputing institute in Indiana. And then what image types are involved, both calibration science images, and these have to be separated by filter and block. And then PSF has to be generated, goes to RA and DEC, and you want to calculate so-called growth curves and aperture, which are aperture corrections, and apply standard air mass and extinction corrections. And these are done with both of these types of data, and then you run the this is the point where you would run the crowded field photometry code. And finally, you have to create these catalogs, match all of the objects, merge photometry, normalize all the 0 points, and apply color terms and get to the absolute calibration, and do this over a large area of sky, 200 square degrees, a large stellar area of sky. Now, this has been done in the Dark Energy Survey, the main survey of the Dark Energy collaboration, but we did this as a small group. And this is to give an idea of some of the challenges here. You'll notice that because of some data being taken in non-photometric conditions, it was necessary to do essentially a photometric transfer from the photometric data to the non-photometric data, so that everything that is data taken when there were some clouds, and to basically get everything on a final photometric 0 points. And this is described in the 2022 paper. So this is a map of point source detections. And so the algorithm did not fail in even the most crowded fields. So this is going from minus 12 degrees to minus 2 degrees at the top of the frame here. So we're going toward the galactic plane and increased crowding as we move toward the top of this image. And you could see that we even detect these dark clouds very clearly. We do have some missing data and so on, but relatively we recover a contiguous map of star density in the galactic bulge. And then you could see these are the 62 CCVs and a zoom in on a globular cluster. So this is actually delivering actual point spread function fitting photometry over this large area of the sky. Again, this shows the extinction maps. And this is something that for the portion of LSST science that addresses the galactic plane, a concern will be the extinction correction. And here you could see that we have EU minus I mapped here. So there's significant extinction for the plane. So how did we derive these extinction maps? We actually had to go to studies of the red clump using the BDBS survey. And Yulia Simeon had derived a 1 arc-minute by 1 arc-minute grid of reddening for that survey. It would be possible using probably I and Z, we are actually working on that now, to do a similar reddening map. The method is that red clump stars largely have a red clump star is a helium burning red giant. And these stars have roughly the same color. They're called a clump because they bunch up on the red giant branch. And this is due to the fact that the star that has undergone the helium flash at the tip of the red giant branch is now burning helium in its core and hydrogen in a shell around that core. The core is roughly half a solar mass, and the 3 alpha process provides there is enough fuel for the star to live roughly 100 million years. Now, this is longer than the red giant that is on first descent, and so therefore, there will be a pause of such stars. They will be living in the red clump condition, and that is why it's called the red clump. There are just a lot of those stars at that luminosity because they have access to the hydrogen, to that helium burning main sequence phase, as we call it. You can see this is how the red clump appears in the color magnitude diagram in excess of stars relative to the first descent red giants. Now, this shows that we
Michael, you are at the 18 minutes mark.
Oh, thank you. Okay, well then I'll try to speed up here. And so we got all these beautiful color magnitude diagrams. So anywhere in the bulge, you can get a de-reddened color magnitude diagram. And we also were able to match to Gaia DR3. This is something that, of course, LSST will want to do this and will want to also extend Gaia beyond the end of the mission. That's an important problem. There's a good review article by Ivazic discussing that annual reviews, and this shows an example CMD with a claim from Saha et al. That there are young stars in the bulge, and we were able to show that these alleged young stars in the bulge are actually not blue loop stars, which are massive helium burning stars of 3 solar masses. Rather, they are foreground disk red giants, so that are essentially foreground clump giants. We also detect the Sagittarius dwarf spheroidal in the vector point plot. And we also found that a candidate dwarf spheroidal galaxy is actually a metal core globular cluster. This is FSR 1758. There were some claimed globular clusters. Minity 22 turned out not to be an actual globular cluster that actually had its own FJ letter. And the same fate for a number of other Minity clusters. Actually, Granite had also found that these were not real clusters. The most important result has been with respect to metallicity. There have been multiple claims in the literature for different peaks of metallicity in the bulge from various spectroscopic surveys. And this is one based on those very same microlens dwarfs. Multiple peaks of metallicity here, multiple peaks of metallicity in Ness et al. 2013. All of these authors tend to like to fit Gauss things, and I call this as the Martini rule, that 1 martini is great, 2 can be even better, and 3 is far too many. And so we use the U-band, and this is very significant for LSST. The U-band can provide useful photometric metallicities, even as high as Fe/H plus 0.5. This shows the absorption due to iron 1 lines as a function of metallicity. So you may be aware that in the 1950s, astronomers used an index called delta U minus B. to derive correlated with metallicity, or the delta U index, delta UV index. Well, this was used at that time for stars below Fe over H minus 2.0. Now we find that we can get a calibration that works at plus 0.5 dex. Now these are red clump stars, and we correlate them high resolution derived metallicities, either from calcium triplet or classical high resolution spectroscopy. And we were able to correlate U minus I D redden versus Fe over H and get a 0.2 dex scatter. And we were able to do this in 3 fields with red clump stars at different galactic latitudes and different reddening. So high reddening here, low reddening down here. Beautiful correlation. Out the other end has been a metallicity distribution function. And this is the metallicities derived from classical spectroscopy, this abundance distribution, and in gray is our photometric metallicity distribution. This is a bit of a joke here where we fit our distribution shape to an elephant that has been swallowed by a python in The Little Prince, but I'll skip through that. What we were able to do, and this is our core result, and you could just let me know 1 minute and I'll wrap up at that point. But what we find is that
you have 2 minutes with questions.
Okay, I will wrap up at this point. Low latitude metallicities look like the simple model of chemical evolution. As you move out to outer latitudes, you see a opposite degraded peak, lower metallicity peak, and a bimodal distribution here. None of these are Gaussian distributions, and we are still trying to interpret these in terms of chemical evolution. We now have 3 million metallicities done this way, and this is our current metallicity distribution going from -4 dex out to -10 degrees. Okay, I'll end here, but I wanted to thank you, the Simon Heisings Foundation, for support, and we are trying to get our crowded field results. We are determined to get a result. Sorry, I don't have that to present here.
No, this is great. Thank you so much. These are Kickstarter projects, so you kickstarted it. So I think it fulfills all the requirements that we had.
Well, thank you so much. And we also hope that once everything is safe and good to go, that we'll bring some students from Concepcion to UCLA.
Indeed, that sounds great. We have time perhaps for one quick question. If anybody wants to unmute and ask it in the next couple of seconds. Perhaps I gave the impression that we were on the timeline already. So let's thank again Michael for this presentation. We look forward to inviting you again to tell us about the results when they're available and tell us about the experience of the students that come visit you from Concepcion. So thanks again. Virtual or physical rounds of applause, please, for Michael. And with that, we can move on to, there was actually a question on the chat. Michael, I invite you to look at the Zoom chat and perhaps answer it there in the interest of time.
Oh, sure. I'm happy to. And if you have other questions, please post them on the chat. And I'll answer.
Wonderful. And also, if you are willing to, let's continue the conversation as well on Slack. So let me introduce the next speaker, Matteo Monelli, who will speak about, sorry, I lost the title of your talk.
It's stellar variability with Rubin-LSST. Pretty sure.
Wonderful, stellar variability with Rubin-LSST. Matteo, you ready to take it away?
I'm trying to share my screen. Can you confirm you see it?
Yeah, I see your screen. I hear you a little bit quiet, so just make sure that you speak into the microphone. It was going kind of in and out.
Yes.
And now we see it in presentation mode.
Okay. Okay.
You're good to go. You have 25 minutes total.
Okay. Yes, I also start thanking the Eisen-Simons Foundation because without this support, we wouldn't have done at all this project. So we are really happy. We show here some of the first results. Some have been already presented in previous meetings, but I will show you some of the new stuff that we've been working on in the last few weeks. So the team was made initially by myself, Massimo Dall'Ora, and Jorge Casares, who is with me here at the ISC in Tenerife. So to give a bit of background, myself and Massimo have a very similar scientific interests in resolved stellar population, variable stars, especially pulsating variable stars, and especially RLI and Cepheid, and globular clusters and stellar photometry. While Jorge Casares has a different background because he works with black holes and binary system. So we decided to join and to try to see stellar variability from different expertise. We are used to pulsating stars, he used to other kind of variable stars. And then Barthélemy Dans, that was my master student that has worked a little bit on the data I'm going to present you today. So we had three main objectives, say, in the project proposal. The first work, well, basically everything was devoted to be prepared to use Rubin-LSST data and to exploit them to study stellar pulsation and variable stars in general. So we all know that there will be a flood of alerts and a flood of data to analyze. So we started thinking how to do it, how to approach it, and to develop tools to optimize this kind of analysis. And so we were seeking for testing existing codes for identifying variable sources, and the three basic aspects of the analysis, which is finding the period, characterize, so determining amplitudes and magnitude, for example, and classify them, which are kind of independent but tightly interconnected things to do. And we've been working with also within the framework of the DBS, and especially the Crowded Field Photometry Task Force. And namely, we have worked with the DECam data for a globular cluster, NGC 6559, that has been mentioned already by Michael before, and the data for the galactic disk. So there were basically independent lines, but with a common objective. And the long-term idea that we are interested in is exploiting Rubin-LSST data, and here I list only three of the many projects that we would like to do in the coming years. So Massimo is especially interested in the stellar population and the RLI star population in the bulge. I am also interested in more in the halo than in the bulge, so tracing the halo to the farther distance, and in the RLI stars in all local group galaxies, and especially the Milky Way satellites that will be beautifully traced by LSST. So the first point, we started making tests with the DP 0.1, and especially we took one of the notebooks that were available, the one that were focused in looking for variability, and we tried to improve it. And so we played a little bit with the algorithms for finding the period, with the the interpolation of the light curve. And here you see on the bottom right panel, a fit of the light curves made with spline. But these are, I mean, these results have already been presented, so I'll go quickly through them. And in a way, we are not there yet, but our objective is to make this improved notebook public. So we are not software engineers, so we are not really proud of our writing software, but we are very sure that we'll be able to share this very soon. Okay. The second topic that especially Massimo has worked a lot on is this cluster, NGC 6569, sorry. And because this is a beautiful example of crowded field, as already mentioned by Michael before. So you see here the cluster. This is one of the DECam chip where the cluster is located, and you really see this carpet of stars. So these are challenging fields for data reduction because of the stellar confusion. And we've done a lot of work that Massimo has already presented many times in the TVS meeting and also at the recent LSST at Europe Congress in Rome. So I will just briefly mention some of the results that we attained. So we have made a lot of work to have an optimal photometry with ALLFRAME. So ALLFRAME is an old code, if you want, because it's been developed in the 90s, but it's still the state of the art for photometry in crowded field, because it takes the information from all the sources in all the images simultaneously. So it goes, it's an alternative, it goes a little bit beyond the forced photometry, because it tries to fit an input list of stars simultaneously in all your data. And we are doing right now some comparison with the DIA photometry. We've also analyzed variable stars. So this field has already been observed by Ogle. So there was a pretty complete list of variable stars in the field, but we have found a new object, including Aralides that are here in red in the horizontal branch of the clusters, and also Delta Scuti and the Eclipse in binaries. So this, of course, is deeply embedded in the field of the Milky Way. That's why you don't see a clear sequence for the cluster, and also because it suffers for quite strong differential reddening. So we're also working on our own reddening map. And here you see a couple of examples of that. Because if you want more details, you can find the presentation given by Massimo in multiple locations. So I want to focus more on the third set of data that we've been working on. Again, these are DECam data, and this was one field in the disk. So it's a pretty nicely crowded field, but not as crowded as the bulge. So here you see the full set of CCDs. So these data were observed by Jorge Casares, and the scientific interest of this data was one specific binary. I don't know if you see my mouse, but I mean, they were interested in one binary stars with candidate black hole in the center of the DECam field. So everything else came for free. And what they did was to observe them for 2 consecutive nights in 2 bands, R and H alpha, basically alternating R and H alpha continuously. And they also took a few I-band images just for having the color information. So this was a pretty nice data set, and we were, curious to see what happens for various reasons. Well, first, because we are not used to observe the disk of the Milky Way with such data. We are more used to globular clusters or to external galaxies of the Milky Way. So we're really curious to see what kind of variable population we could find. We would expect Aralides and Delta Scuti. I was expecting personally a lot of Aralides stars there. And also, we were particularly intrigued by the H alpha because I had never seen personally any time series in H alpha for classical pulsators. So we were really curious to see what would came out from the data. So here you see these are a sort of true color images, not true color because the R and H alpha are quite degenerate, but it's a composite image of one of the chips. And you see that there is strong features on the dust, this patchy dust gas distribution that introduces a lot of differential reddening. And you see another zoom here, in which you can have an idea of the kind of crowding that the image has. These are crowded, but it's not so severe. You see a lot of black spot between the stars. So we are in a region that is still doable. And what we do for the data reduction is a standard Daophot frame approach. Basically, we iterate to successive level of complexity. So we first reduce images one by one. We try to perform a first PSF. We have an automatic routine in places since years that try to pick up the best stars to model a PSF. Of course, the standard approach to look for bright isolated stars does not work here because there are no isolated stars at all. So the point here is not to look for isolated stars, but to look for bright stars that cover the whole chip and to iterate. So you make star isolate by subtracting the neighbors. And by proceeding 2 or 3 or 4 times, you are able to get to a very good list of stars to have a very good PSL. And then we usually stack all the images to make the deepest possible list of sources. Then we feed ALLFRAME with this list of stars, basically. And on average, we are obtaining of the order of 45,000 stars per chip. We have made a photometric calibration using DECaps for the R band, using basically a 0 point. We didn't find a color term. We have not calibrated yet the H alpha because we don't have a local standard. We have not been able to find standard yet. So in the next plot, you will see, well, basically the H alpha shifted by an arbitrary 0 point close to the R. Okay, the second step was the search for variable stars. And in this case, we use the Welch-Stenson index. This uses the fact that the light variation is correlated in different filters. So if you have ideally simultaneous observation in multiple bands or close observation, as this is the case, because if we have alternate R and H alpha images, you can exploit the fact that when the variable star is far from the mean, you will have a large difference in magnitude in measurement close in time. So you can build an index that presents basically 0 for non-variable stars and a high value for variable stars. How large? It depends. It's not easy to find an absolute threshold, but in this case, I've seen that Welch-Stenson index larger than 1 is pretty safe not to lose stars, and we have very few confirmed variables between 0.9 and 1. So with this selection, we had of the order of 300 to 500 candidate variable stars per chips. And then we expect visually all the light curves and remove the outliers, saturated stars or star close to the edges, or defects, or simply non-variable stars. And we end up with more or less an average of 60 confirmed variable object per chip. Yeah, between 55 and 65 on average. Okay, so some of the light curves. So I was a bit surprised because the vast majority of the sources that we find are binaries. Probably it's not surprising, but I was really surprised that 80% of the variable stars we find are binaries, and we have all sort of light curves. So you receive from detached, semi-detached to contact binaries. So we have really a huge variety of morphology of light curves. Of course, we are limited by the sampling of the data. We have only 2 nights, so the majority of these variables present short period. We are, I think, quite blind to variables with longer period. Then we found I think this is pretty interesting. So I have no idea what they are. So if any of you have idea or suggestion to classify this object, I'm really welcome to talk to you. So basically what we see here, 2 examples of 2 stars. So on the top is, no, this is not phased light curves. This is simply magnitude as a function of time. You clearly see the 2 chunks of data of the 2 consecutive nights. Basically, there are a few stars per chip that present correlated variation in the 2 filters, but it is basically impossible to find a period because the amplitude changes, the period between the peaks changes. So recently, when I was realizing this chip, I noticed that many of these objects are located in pretty crowded regions. So I thought, oh, okay, so this must be this mirroring effect of crowding, and what we are seeing here is the effect of seeing. But the seeing has been pretty stable over the 2 nights, but not perfectly stable. So it was varying between 0.8 and 1.1 more or less. But if you compare different stars, you see that the pattern is not consistent. So I would expect that if we are seeing the effect of seeing, the peak should be more or less at the same time of the night, in coincidence of the best or worst seeing, but this is not the case. I mean, every object is going up and down with different patterns. They are not correlated at all. So also, they are not especially blue object. They are in the bulk of the color diagram. So I don't think they are a clear example of sorry, I missed the word now. Cataclysmic variables. Okay, now I would like to stop my presentation for a second and share with you, to make this a bit more dynamic, some real example of how we work with the light curves. So we do it still in a really handcraft way. So we check light curves one by one. So I would like to start with, let me see, I'll explain in a second what you are looking at. Just let me find the star I wanted you to see first. It should be this one. Yes, this one. Okay, so this is a code that was developed by one of our students, well, a few years ago. It was 15 years ago. This was optimized for RRI stars in external galaxies with HST data. So it works optimally with not so many points, of the order 20, 30, that cover nicely the light curving phase. So for many of the targets on the low period, the small period target here, it works pretty well. So what you see here is, well, an image of the star, which are really useful when you have a lot of candidates to remove background galaxies, cosmic rays, defects, saturated stars, a profile of the object, and isocontours. Here on the right panel, you have the periodogram, which is basically the Fourier transform of the data. And the program automatically selects the peaks in this plane and plots on the right the phased light curves. So the period corresponding to the most probable value is used to plot the phased light curve. Here we have two panels because we have two filters. So R is on the top and the H alpha is on the bottom. And we can fit here the light curve in a template. You see, this is a very small amplitude variable. It's below 0.1, it's 0.08 and 0.07. So another very useful piece of information is when you plot the magnitude versus time. So this is the
Matteo,
yes.
this is your 18 minutes marked.
Okay,
warning.
great. Thanks. So here you see magnitude versus time, and here you see the wiggles. This is the star with the shorter period that I found is 0.06 days. You really see the stars going up and down, up and down. So the message of this this screen is that you need a lot of complementary information. We also have the column diagram here, but since the R and H alpha really degenerate, it is not really useful in this case. But if you have a globular cluster to check if a star is on the horizontal branch as an RRR is expected to be, is really useful. So using all these constraints, we are help to classify. The other thing I wanted to show you are some example of badly behaving stars like this. So this is one of the star I showed you before, the one that flickers up and down, and basically it has a noisy periodogram that is basically impossible to see what the period is. I mean, you can choose any of the peaks, and basically you never find the light curve. So if you have ideas of what these sources can be, they all look like stars. As I was mentioning before, they are always somehow, there are hints of blend, but I don't know if this can explain the issue. The other interesting object are some example of eclipsing binaries. This one. Um, But okay, basically, the thing I noticed, and I think it can be useful for other people working on classification. Well, here you see the periodogram with a clear peak, and you see a reasonable light curve. But there are a significant fraction of cases in which the code is picking up an alias. So you see that the light curve here is not perfect. And indeed, if we force the program to fit the light curve with the double of the period, and then we adjust it a little bit. Okay, this looks much more reasonable. So an automatic selection of the period from the periodogram would give you the wrong period in this case. And there are many other examples like this one. So I had no experience with this kind of stars before, so I realized that this can be an issue. And this happens because the two minima, of course, when the two eclipse, so one stars pass in front of the other. So of course they are tracing half of the period of the orbital period of the source. And these are easy to detect by eye when the two minima have different depth. So okay, this one is another obvious case. You clearly see here that there is a split, and this is telling you that the period is wrong. So 60. Okay, so these are examples I wanted to show you. And I go back to the presentation. Yeah.
There's about 2 minutes to the hour, so if you want to
Yes.
take questions.
I just wanted
No.
to show you one more thing.
Okay.
It's about RLI stars because, okay, so I found well-behaved RLI stars like this. And then when I go quickly to the comparison with Gaia, okay, in this case, okay, we have a nice comparison, but then Gaia was giving me other sources that were not at all variable in my photometry. So I got a bit worried. So these are really the last week work. And indeed, if you take the Gaia photometry, they are not convincing at all either. The thing is that they are really faint. We are about magnitude 20, 20.5. And indeed, about the 400 RLI stars that Gaia says that are in this DECam field, the majority have very faint magnitude, very close to the limit of Gaia. So I think this will require a lot of extra work to check them one by one. So this is, I think we did the comparison properly. We did the match by coordinates. So I don't know. There's something to look at. And okay, I'll leave the conclusion here and I'll take your questions. Thanks.
Thank you, Matteo. Thank you very much. A virtual round of applause for Matteo as well. We are just about the top of the hour. Maybe we'll take one quick question. I saw some conversations in the Slack with Michael Rich, who was the earlier presenter. Thank you very much for keeping up the conversation. And yes, I see that Michael has his hand up.
Did you find any, I noticed you didn't find any eclipsing binaries. I was wondering if, you were sensitive to eclipsing binaries. And by the way, I have to compliment you. This is a really beautiful result and very impressive. What was the galactic latitude, longitude again in the field? Galactic latitude was presumably 0, but the longitude?
No, it's not that close to the plane. It's -4.
And longitude?
I don't remember that. I can give you a Ryan deck.
Yeah.
Right now it's 231 minus 61.
Okay. Okay.
Roughly.
Wow. So very nice. And you didn't find any eclipsing binaries?
Yeah, we find many actually.
Oh.
I mean,
There's
So
another
that-
hand raised by Liliana.
no, yeah, like
Perhaps
this.
as we see
Oh, those are
these,
contact binaries. Okay.
Yes.
Okay. Answer
perhaps
really
as we see some more
Yes.
slides, we can let Liliana ask a
Sure.
quick second question before we close.
Hello, very nice talk. Thank you. I just wanted to know if you found transients apart from the variable sources that you
No.
discussed. No. Okay.
No.
Okay, okay. And any of the binary that could like have white dwarf, like cataclysmic variables or something like that?
I don't think so.
Okay.
I'm not sure. We are not at the end of the classification and we have still many chips to reduce. But
Okay, thank you.
Interesting. I'm intrigued by that question too, now that you asked it, Liliana. I want to acknowledge that we are at the end of the hour, and I want to, if our speakers need to go, I want to thank them again and tell them that they are, of course, at this point free to go. I did see another hand raise, so if anybody wants to stay and ask more questions, and our speakers are willing to stick around for a few minutes, we can do that. But yes, first of all, thanks again, Michael and Matteo. Thank you very much.
yeah, thanks.
Michael, I see your hand is raised, but I also had seen that Jen had her hand raised before I said that we were at the top
My
of the
hand
hour.
is accidentally raised.
Okay.
Yes.
Yeah,
Okay.
great.
So Mario, really great talk. I'm sorry, I had drop off today, so I didn't catch all of it, and I missed Michael's, unfortunately. But I wanted to ask, so with regard to identifications and stuff like that, how much of this are you relying on previous experience with Kepler, K2, and TESS? Do you see what I mean? Because specifically for your R. Leary and some of your other curves, I think that there's a wealth of knowledge to draw upon. But before I wanted to expand on that, I just wanted to ask, yeah, are you drawing upon these sources or not? Yeah.
So right now we are doing things blind, in the sense that we also want to see, our final list, what, I mean, a posteriori, what has in common with other experiments of the same fields.
Well, I'm
And-
sorry. What I mean is, I mean the actual algorithms themselves, as opposed, because there's not much overlap
sorry.
in magnitude space, right, between the two, unfortunately. But yeah, so algorithm-wise, are you drawing upon the bulk of the community, kind of information on this stuff? Because for instance, identification of BBs, there's a whole host of resources I could think of right now that might help with that.
Okay. Now, well, so far we are doing things with the things we know, but yeah, later we would like to expand to other algorithms and share what we have, of course, if it can be useful.
But
Thank you.
regardless, this is just really nice work. Thank you.
Thanks.
Thanks, everybody. Thank you to Michael and Matteo, our speakers. Thanks, everybody who participated. Don't forget to check the TVS calendar for the future instances of the Kickstarter Colloquia series. And have a great holiday break. Bye-bye, everybody.
Thank you very much.
Thank you.
Bye-bye. Thank you.
Bye.